One of the new things at Carnegie over the last decade has been the development of a theoretical program. You've heard some of our theorists before, Gina Kohlmeyer and Andrew Benson. And tonight's speaker, Tony Piro, is the latest staff hire in that area of theoretical astrophysics. And Tony is the world's expert on exploding things of all sorts. That's the topic of today. And this is a really exciting field in astronomy because we actually now, from an observational standpoint, astronomers like myself, we now have the ability to find exploding stars in very short time periods, even sometimes almost before they've exploded. So, and you'll hear about that in Tony's lecture today. Where is Tony? Is he somewhere in here? He's in the back. He's hiding. Okay. So with no further ado, let me introduce tonight's speaker to you, Tony Piro. Tony? There he is. I forgot where you were at. How's that?
Great, thank you. So I'm really excited to be here tonight and talk about one of my favorite topics, and that's things that explode, like John said. So we're going to talk about some of the most fantastic explosions in the universe, supernovae. And so our story starts this night, February 24th, 1987. This is a little over 30 years ago. And here's a view of Las Campanas Observatory. This is, of course, the mountain, the observatory run by Carnegie Observatories. And this is an especially glorious looking night. You can see, the Milky Way overhead right here. You can even see a comet right here. And also I want to point out, we also have these two nearby galaxies. So these are some of our Milky Way's nearest neighbors. These are the small and the Magellanic Clouds, the large Magellanic Clouds. The large Magellanic Cloud is merely 160,000 light years away. The small Magellanic Cloud's 200,000 light years away, so just a small distance in astronomical terms, okay? And inside the Large Magellanic Cloud, there's a region called the Tarantula Nebula, okay? And this is a region where a nursery, where young stars are being born. See, aren't they cute, these little baby stars in here? And on this night, something new was seen near the Tarantula Nebula. Right here. One star had become as bright as about 250 million suns. So this is a supernovae. And this was discovered by our own Oscar Duhalde and Ian Shelton, who were working up at Las Campanas Observatory at the time. And they had seen, Oscar had seen with his naked eye the first supernova that somebody could see this way in almost 400 years. Okay, this is the most nearby supernova we've seen in almost 400 years. And so right in this one event, this explosion released as much energy as the sun would release during its entire lifetime, it radiated in its entire lifetime, just in this one event. Okay, and because it was so nearby, it really revolutionized our understanding of supernovae because it was the first one in kind of modern times where we could use our modern technology to study it, and we learned so much from it. And I remember at the time, actually, I was 8 years old when this happened. And at that age, I couldn't appreciate all the implications of what everyone was learning, but definitely I could feel all the excitement that was happening at the time. And it's amazing to think all these years later, now it's actually my job, if you could call it that I get to actually study these same supernovae now. Okay, so what are these supernovae? Let's kind of start at square one. So where does this word come from? It's a combination of two words, the word nova, which is Latin for new, so it's like a new star in the sky, and super, because they're really freaking awesome. They're these humongous explosions, right? So they're super. And this term was actually coined by Walter Baade and Fritz Zwicky. So here's some nice pictures of them here. So again, there's all these neat connections with Carnegie. So Walter Baade was actually a staff scientist at the Carnegie Observatories. Fritz Zwicky was actually a professor at Caltech, but they worked together a lot in Mount Wilson. And in 1934, they wrote this really seminal paper that was just really ahead of its time, where they talked about these supernovae. Back then, they had a hyphen in it. And they talked about how these were probably the ends of the life of stars. And they even speculated some things like there might be a remnant left over after the explosion, which is something we'll discuss later in the talk. Okay. As I mentioned before, the explosions can become as bright as 100 million to 1 billion stars. And this lasts for about a few weeks to months. And a given galaxy like our Milky Way will typically have one of these supernovae once or twice per century. And so because of this, we've actually been seeing supernovae in our galaxy for a long time. And so the first historical record, as far as I know, was in the year 185 AD. The Chinese had records of a new star in the sky. There's also extensive records of a supernova in 1054 AD that was described in this Chinese writing. And even today now, we can see the remnants of this supernova. So this is looking out at our galaxy with, of course, modern technology. We can see basically all the shrapnel blowing away from this explosion that happened about 1,000 years ago. Okay. Now, you don't want to have to wait 100 years or so to see a new supernova every time, right? But luckily, they're very bright, and we can study them in other galaxies. So here's some various galaxies fairly nearby. You can see in each of these there's this bright, almost looks like a star, but in each case, this is an exploding star. This is a supernova in each case. In this galaxy, they had a supernova in 1999, in 2007, and 2008. So this must have been an especially exciting galaxy to live in. So if only we could be so lucky, right? Okay. And as technology increases, we can find more and more of these supernovae. So here's just this montage of all these, each of these images is a different galaxy with a bright spot that's identified as a supernova in it. So we're able to study these all across the universe and just learn tons of information. Okay. So one of the things that really interests me about supernovae is they kind of have this dual nature. On one hand, they're just incredibly destructive, right? These are some of the biggest explosions in the universe, right? I mean, seriously, you don't want to be living on this planet when this happens, right? And this is just nearby. This effect can be felt on much larger scales. And so here's an example of a galaxy where you've had many of these supernovae happening over and over again for millions of years. And from all this input of energy, you can see this is like the plane of a galaxy, like a disk galaxy looking edge on. And this is material being blown out of the galaxy due to all the supernovae that are going off. So you can just have effects on massive scales. These are tens of thousands of light years across that you're having material blowing out of these galaxies. Okay, so they're incredibly destructive, but at the same time, they're fundamental for creation. And so here's a look at the periodic table. You might remember this from high school chemistry. Hopefully I'm not triggering any post-traumatic stress by showing this. And the key point here is that here's the periodic table, and it's color-coded by where in the universe these different elements come from. And so you can see in the Big Bang, mostly only created hydrogen and helium, roughly. And then I just want to highlight, look at all this blue stuff here is stuff that's synthesized during these explosions, okay? Things like nickel and cobalt and copper and all sorts of cool stuff. But there's also another important point. So all this stuff here in yellow, this is stuff that's generated in the cores of stars as they're burning material. But that stuff can't stay in the stars, right? It eventually has to get out to make new generations of stars, right? And the only way for that material to get out is through supernovae. So in some sense, supernovae are basically responsible for us having all the elements here in the periodic table. Otherwise, we wouldn't have these. So it's just really fundamental. And so what happens is, as a supernova will explode, it will compress the gas around it, as shown here. And as it rips through this gas, it compresses it, causing gravitational instabilities, so that you have the next generation of stars forming, fundamental for the creation of new stars. And these stars are enriched by all these heavy elements that were generated in the supernova, so now you can make new planetary systems, new Earths that require things like silicon and iron and all the stuff generated in the supernova. And now you have all the important complex heavy elements and building blocks, so you can have things like life that wouldn't exist without these supernovae. Okay. So supernovae are just fundamental for the universe, but this begs a lot of important questions about them. So what are these mysteries? Which stars are actually exploding? Why are some of these stars exploding? And what triggers the explosions? Why would a star living happily for millions of years or billions of years suddenly just explode so violently? And so like any good detective, we need to look for some clues, all right? And so what do you usually do? You go to the crime scene and you look for some evidence, right? Okay, we all know these. And so what kind of evidence do we look for in the case of the supernovae? So here's a looping movie. It's only a few seconds long, but what I want you to see is there's a supernova here, and it's starting to get bright, and then it gets dim again, and then it loops again. So you can see it getting bright and dim, okay? So the amount of light coming out of the supernova over time is changing. And so you can imagine making a plot of, over time, how bright is the supernova. This is called a light curve. And this encodes a lot of important information about the explosion. And so here's some plots I'm going to show. So unfortunately, John mentioned I'm a theorist. And so I'm not going to go easy on you guys. You're going to see some plots today. You might even see some equations. So this is time here on this graph. And this is how luminous it is in units of the luminosity of our sun. So here is 100 million times the luminosity of our sun. Here's 1 billion times the luminosity of our sun. Okay? And so what you do is you graph how the luminosity is changing over time for one of these things, and you get a plot that looks like this. And so you can see, kind of like I showed in the movie before, it gets bright for a while, gets dim. Oops. That's good. So, and you see it took about 2 weeks or so to get to the maximum brightness for this guy. And it became about 2 billion times as bright as the sun. Okay. And so we'll see more and more of these supernovae and make plots like this, and we see, hey, a lot of them have a shape of their light curve like this. This is interesting evidence for how this explosion is happening. But then we start looking at some other ones, and they have light curves that look like this. So it goes up, and it kind of flattens out for about 3 months or so, typically. It's the kind of typical length scale, and then it kind of falls off, and then the supernova is over. These ones don't get as bright. So and we've looked at these over and over again, and most of the supernovae we see seem to fall into these two classes. And so now we have some of the brightest explosions in the universe, these awe-inspiring events, and we see two different classes. So we should name them something, right? So what do you think we've named them? Well, these are called type 1. And these are called type 2. We're astronomers, we're not poets, right? So what do you expect? And so just to clarify things, there's actually more subclasses than this. I'm just kind of giving you guys a rough idea. But to be more precise, these are typically referred to as type 1As in the literature. So I'm going to use that name. But there's basically two classes. That's the key point. All right, so that's the first piece of evidence. The second is, just like a good detective, you want to look for some fingerprints, right? So what's analogous to fingerprints for a supernova? So what we do is we actually look at the spectra. We split up the light into its constituents, different wavelengths of light, different colors, and we look at how much light there is at different colors. And so you get these complicated plots that look something like this. This is what you see for a type 1A. This is the wavelength of light you're looking at. So this is going from blue light here, greenish light, to red light. And you look at how bright it is at each of those types of light. And you see this pattern here. And from this is basically like a fingerprint of the elements that are in the explosion. We can figure out what the explosion was made out of. And so we've identified some of them here. You can see things like silicon and iron, Fe is iron, and oxygen and some calcium. And so this is the fingerprint you see for this explosion. When you look at the type 2s, they look very different. Okay, not only the shape's different, but the elements are completely different. Instead of seeing all these silicon and iron, you see a lot of hydrogen around, which is never seen in the type 1As. So this is another important clue. The composition of the explosion itself is completely different in these two cases. Lastly, you want to look at the location of the crime scene, right? That might give you some clues about what happened. And same thing here. So there's the host galaxies. What kind of environments are these supernovae happening in? In the case of the type 1As, you have galaxies that look kind of like this a lot of the times. These are called elliptical galaxies, and they're mostly older stars. You can see it's not very bright and blue. And this is different than the type 2s. They tend to happen in these galaxies more like this. This is kind of these classic spirals that you know and love. Lots of bright blue young stars, lots of stars being formed here. The type 1As can happen in each case, but the type 2s always happen near these young stars. So another important clue. So let's just review these. So the type 1As and the type 2s have different light curves. These are short peak light curves. Type 2s have these long flat ones. Lots of silicon and iron generated in these explosions with no hydrogen, while the type 2s have lots of hydrogen present. And then the environments are different. The type 1As are located both next to young and old stars, where the type 2s are specifically with young massive stars. Okay. So using these clues now, we can try to figure out what the actual progenitors of these explosions are. And we're going to start with the type 1As. Given all these clues, what the astronomers have concluded is that type 1As are actually from a type of star called a white dwarf. So here's a white dwarf here. White dwarfs are the burned out cores, the old cores left over from stars like our sun after they exhausted their fuel. And what's important about them is they don't have any hydrogen. They're basically carbon oxygen. They're from the core of our sun, a star like our sun. And so that's why they don't see any hydrogen in the explosion. And they can be very old. You have to wait for billions of years for a star to make a white dwarf before you can have it explode. And so again, this is why we see them in old environments. So why would a white dwarf explode? Well, what happens is these white dwarfs can often be in binary systems where they can gain mass from another star. And as they gain mass, it compresses the core of the star. And so these are systems like this. So this is this neat animation where this is a white dwarf here. And here's a star like our sun. And it's donating material to the white dwarf over millions of years. Okay. And what you'll see is over time, the white dwarf gains mass and gets compressed and compressed until it gets so hot in the center, up to 1 billion degrees, that the carbon in the center ignites like a giant thermonuclear bomb. And that's what we think makes a type 1A supernova. Okay? And so we can understand this in even more detail using theory. I'm a theorist, like it's been mentioned. You can imagine, what the heck does a theorist do all day? Even my family, I think, wonders what I do all day sometimes. Okay, so I just want to give you a flavor of what I do. So typically, I start off by doing a lot of math. So here's some of my notes. Okay, so my office is full of notebooks full of scribbles that look something like this. Look very carefully because you'll be tested on this at the end of the talk. Okay? And sometimes we can solve these equations with pencil and paper. Other times the equations get too difficult to solve, so once we had a set of equations, we'll write computer programs to try to help us solve them. So there's lots of exciting looking code like this that you get to debug all day. But the end result is then you can simulate different parts of the explosion and understand in more detail what was actually happening. And so here's a result of one of these simulations. This is a plot of a white dwarf from the inside at 0 out to the outside. This is the surface of the white dwarf here. And then this is mass fractions of different types of materials. So the higher the line is on this plot, the more of that kind of material there is. And you can see there's carbon, oxygen, neon, silicon, sulfur, all your favorite elements from the periodic table. The white dwarf, you can see, is mostly composed of carbon, which is this kind of pinkish line here, and this greenish line, oxygen. They're roughly equal amounts inside the white dwarf. And so what we can do is now set this up on the computer and have the star explode and see what it generates. Okay, so now the explosion is proceeding. It starts off rather slow and then accelerates as the star starts burning up. And you can see all these heavy elements that are getting generated in the explosion. There's temperatures of around 1 billion degrees being generated inside of here. Okay. And so in real life, we actually had to slow this down to show this to you. It only took about 1.5 seconds for the explosion to proceed through a star that was roughly the size of the Earth and the mass of the Sun. 1.5 seconds. And you can see all the interesting stuff that was generated inside of this white dwarf. You can see here, this yellow is silicon. Remember, that was one of the predominant elements that we saw in the observations. When we do our simulations, we can confirm that you expect a lot of silicon being generated in the explosions. Some other important ones are different types of iron that are seen down in the core, as seen in the observations. And you can see this white line is the most prominent. This is nickel 56. This is a certain isotope of the element of nickel. And this will play an important role later on, so we'll come back to it. Okay? But in this way, we can actually use the observations and compare with them and see if our theory is predicting the right things so that we see if we really understand these explosions fully. So as if it wasn't enough for these type 1As to generate all these important elements necessary for life and everything else in the universe, these type 1A supernovae are also really important as cosmological tools to measure the properties of the universe. And a lot of this work was initiated by a seminal paper by Mark Phillips. So Mark Phillips is, of course, also an astronomer at Carnegie Observatories. He's currently the director at the Las Campanas Observatories in Chile. And in 1993, he made a really important discovery, which we know now as the Phillips relation, but you ask him, he's so modest, he'll say it's the width luminosity relation. He won't call it the Phillips relation, of course. But what he noticed for the type 1As is that there was a correlation between the shape of the light curve and how bright the supernova was. And you can see it right here. Don't worry about what these units are. But you can see the ones that are brighter have a wider light curve, and the ones that get dimmer have narrow light curves. Okay? That's what he noticed. In this paper he wrote in 1993, it's probably one of the most well-cited single-author papers I've ever seen, because it's just so important. So why is this important? It means that from the shape of the supernova, you can know how bright it is, right? And if you know how bright it should be, and you observe it at a certain brightness, you can figure out how far away it is, okay? So what Mark has given us is this fantastic way to measure distances in our universe. And so just to kind of show this, so you have different candles, basically. They're basically candles that we have now, standardizable candles, at different luminosities. And now you can figure out, because you know how bright they should be, because you've measured the width of the light curve, you can figure out how far they are away. And you can tell, for example, that this one must be much further than this brighter one you see here. Okay. And so due to this exciting discovery, in the following at 1993, a bunch of astronomers started cataloging a bunch of these type 1A supernovae to measure the size and the expansion history of the universe. And I won't go through all the details, but what they ended up finding was that the universe needed an additional constituent to actually explain how it was expanding, that it was actually accelerating in time. And what we call this is dark energy. So they found, based on these measurements they were making of the size of the universe with supernovae, that 70% of the universe is composed of dark energy. And for this, the 2011 Nobel Prize in Physics was awarded. And so I really love this picture because, of course, the Nobel Prize, they only can award it to 3 people, right? That's just the rules. And so this was awarded to Adam Rees, Brian Schmidt, and then the third person, which I don't have shown here, is Saul Perlmutter. But with a project like this, there's so many other people that contribute. And so what was really fantastic is they were able to bring out a lot of the rest of the team, a lot of the key players, that were fundamental in this discovery, including, you can see in the back, Mark Phillips, for who this wouldn't have happened without what he had done. Okay, so we've talked about supernovae, how they're so bright, how we can actually use them in these different ways. But I haven't actually described to you why would these explosions be so massively bright? Why would they be 1 billion times as bright as the sun? And you might be looking at me like, duh, Tony, it's an explosion. Explosions, that sounds like it should be bright, right? But let's do a thought experiment. Or we'll do a real experiment, actually. Let's say we pierce our lips and we blow out air, and you feel it, and it feels cold. Okay? So what's happening there? Why does the air get cold? It's warm when it's in our mouth, right? As the air expands, it's doing work and cooling off. Okay? And the same thing should happen when a star explodes, right? The star is expanding, it's moving at something like 1/30th the speed of light when it's exploding. And as it expands, it should cool off and become really dim. So dim, in fact, that if this is all that happened, we wouldn't be able to see these in other galaxies. Only the most nearby supernova would be observable because they would cool off so fast. Okay? So the expansion quickly cools the explosion. You actually need, the explosion's not enough. You need another heat source to actually make these things bright enough so that we can observe them in other galaxies. Can anybody guess what you think that other heat source might be? So the clue was, before I mentioned this nickel-56. And so that nickel-56 is special because it's actually radioactive. So you need radioactivity to make supernova this bright. This explosion itself is not enough. And so you have this nickel-56. It looks something like this. It's 28 protons and 28 neutrons. And maybe you remember for chemistry, as you go up the periodic table, typically you get more and more neutrons versus protons. But this has equal protons and neutrons, and that's an unstable situation. And in roughly 9 days, the nickel decays to cobalt-56. This releases energy, which then heats the ejecta. Okay, and this is what's making the supernova bright. It's not the explosion itself. It's glowing because of radioactivity. Okay, but we're not done. The cobalt is also still radioactive. And another 111 days after that, the cobalt decays to iron-56, releasing more energy. And so actually all that nickel that was generated in that explosion turns into iron. Iron that's fundamental for making the buildings around us, making magnets. For the red blood cells in our bodies is iron that was originally radioactive nickel from type 1a supernova. Okay? And this is what makes the supernova bright. So that's about all I'm going to say about type 1a supernova for now. I want to move on to the type 2s. What's the deal with those guys, right? So just reviewing our table, remember the key points, whereas the type 2s have these different light curves, they have hydrogen present in the explosion, and they're located near young massive stars. And maybe not surprisingly, because of this, we think they're associated with massive young stars. Stars like this, blue supergiants, blue giant stars. So here's like our sun, and so here's a blue giant star. These are typically masses like 10 times the mass of our sun or greater. They'll have radii 5, 8, 10 times the radius of our sun. And you might wonder why I say, oh, they're young stars, but massive, right? You think if you have a massive star with more fuel, it would take longer to burn through the fuel. And it's not actually the case. So the sun right now is 5 billion years old and only about halfway done through its life. Okay? But these blue giant stars, they're so hot inside, even though they have much more fuel than the sun, they actually burn through it much more quickly. So a star like this might have a lifetime of only around 10 million years, which maybe doesn't sound too short to you, but I mean, compared to 5 billion, that's like a blink of the eye, right? And so whenever you have these massive stars dying, they're going to be near other young massive stars. Okay? And so really, these massive stars, these blue giants, live fast and die young. They're the rock stars of the astronomical world. Okay. But that's not all. So these blue giant stars, before they explode, they do other things. So at first, they become red supergiant stars as they're exhausting their fuel. So here's just an example, in case you can't see it. This is a red supergiant. The radius of here is something like 1,000 times the radius of our sun. This would extend out further than the orbit of Jupiter if it was in our solar system. So if you can't see it, here's our sun right here, which is small enough, but here's the blue giant star before that turned into this red supergiant. That's how much its radius has changed. Okay? And if we strip away the outside of this red supergiant, we can look inside of it, and we see this onion layer structure that's really interesting. So what's happened is over time, you've taken the hydrogen you started with and burned it to helium. You take that helium, you burn it to carbon and oxygen. You keep burning the heavier and heavier elements. So near the end of the star's life, you have this onion layer structure. This isn't really to scale. I just want to show you all these different layers forming the inside of the star. And at the very interior, you've burned all the way up to iron. You have this iron core. Okay? Now, this is bad news. You can't burn past the iron. So this is going to be bad times for this star. Okay? So if we look down in the interior, you have, roughly speaking, your hydrogen envelope, this evolved core, and this iron core at the very center. And remember, we needed this nuclear burning to keep the star from collapsing over due to its own gravity. But this iron can't burn any further. It's the end of the line. Okay? And so it can't hold itself up anymore. This core starts collapsing. And everything above it starts collapsing as well. Okay? So it's getting smaller and smaller and collapsing until it gets to this point. When it starts collapsing, the radius of the core is roughly the radius of the Earth. When it gets to this point, the radius is about 30 kilometers, the size of a city. Okay? That's a lot of collapse, and that's happened in less than a second. Okay? At this point, the density of this core is a mere 100 trillion grams per cubic centimeter. What does that even mean? That is the same density as if you took every human being on Earth and packed them into a sugar cube. That's the density of this entire core that's roughly 1.5 times the mass of our sun. Okay? And it's at this point that the core realizes it can't collapse any further. There's nuclear forces that prevent any further collapse. And so it becomes stiff. But all this other stuff on top of it wants to still collapse. So what happens is it actually bounces off of the core and it starts hitting other material. So all this material is smacking the core, bouncing off of it, and expanding out, ejecting the entire star. And this is what powers these types of explosions. We call it core collapse explosions. These are the type 2 explosions. And all that's left over is this core, which we know as a neutron star. And in fact, we know about thousands of these neutron stars throughout our galaxy, which are the remnants for all these type 2 supernova explosions. And even if we look at, remember that supernova from the year 1054 AD, shown right here, if we look inside the ejecta in X-rays, we actually can see a neutron star living inside of there, the remnant core from that star that exploded about 1,000 years ago. Okay. So again, I'm a theorist, so what kind of stuff can we do with theory to try to understand these explosions better? So we do simulations that look something like this. So what we're showing here is this is the velocity of the material as a function of mass in the star. So we'll run through it again from the beginning. So you can see the explosion's going to start once this ends. The explosion starts, ejecting all this material, and then you start seeing, this is where you're seeing deeper into the ejecta as the star's expanding, becoming more diffuse. And this is one of these light curves, like I was showing before, one of these flat light curves. And so what we want to do is actually explode red supergiants, make light curves from them in our computers, and see if they match what the observations look like in detail, to see if we're really understanding these explosions the way we think we do. Okay. And so that's what we did here. So these are some extraordinary observations, that's why we chose them, where they have light curves in all different kinds of light. So what these mean is this is the blue light from the explosion, this is the green light, this is red light, this is infrared light. So we have light curves spanning the electromagnetic spectrum, the most detailed information possible so we can compare it with our simulations and see if we really understand these explosions or not. Okay? And so that's what we did, and here's our result. So what do you guys think? We did a pretty good job, right? Maybe? Nah. So at late times, maybe we can match these pretty well. But you can see over the first month or so, the first 30 days, we do a pretty poor job of matching the observations. There's something missing from our simulations that we're not getting to match the observations. Okay? And so we scratched our head about this a long time. You know, when this happens, you're not sure if there's something wrong with your code. Maybe there's some assumption you're putting in initially that's going wrong. What could it be that we're screwing up with these calculations? And then we thought back to that example I was showing before. Remember, the air coming out of your mouth getting cold. So how do we solve this? So remember, as a star explodes, it expands and cools, right? We saw that with the air coming out of our mouth. But if instead of having my lips small together, if I had them wide apart, like, it feels warmer, right? If I start with a larger radius, it's not going to cool as much. Right? So if I start with a larger radius star, it's going to still expand and cool a little bit, but because the initial radius is larger, it's not as much. Okay? And so our idea was, well, looking back to the simulation, right, we were getting too little luminosity at early times. What if we just made the star a little bigger and put some additional material around it so that it wouldn't cool as quickly at the beginning? So what if there's extra stuff around the star? And so that's what we did, and this is the result of the new simulation. So it's not perfect, but you can't blame nature. Nature can't always match what is coming out of our calculations. But you can see adding that additional material around the star did a much better job of matching the observations, right? Okay. And so the question was, is this just in the theorists' heads? We add this material, we get a better match. Does that really prove that it has to be there? And so we were kind of unsure about this because this material hadn't been seen before. But anyway, it seemed really like a good result, so we published it. And only a few months later, there was this exciting paper where they were able to catch a supernova right at the moment of explosion and see evidence through the spectra of dense material around the star, confirming the picture that we had. So this was very gratifying. This was only a few months after our paper came out. Okay? And so all this work has really kind of revolutionized our understanding of these of massive stars and how they end their lives. Just to summarize, these type 2 supernovae light curves really need extra material around the star to explain these explosions. And this indicates that material is being ejected from the star somehow a few months before the explosion. Okay? And what this means is there's some sort of violent activity, maybe some instability in the nuclear burning, we're not really sure, that's causing this material to be ejected right before the explosion. So what is it? Honestly, we don't know yet. This is something we're still trying to understand about the end of the star's lives. So this is ongoing research. But this is really changing our view of how these stars end their lives. Okay. And so everything I've talked about so far has been about type 2s, generating neutron stars. But some of you guys might know that there's also black holes in our galaxy too, right? Where did those come from? We know about these, a few dozen of these in our own galaxy, in systems like this where you have a black hole gaining mass from another star. But these black holes are thought to become from massive stars as well. What are the events that are making black holes rather than neutron stars? And so what should this black hole formation look like? One idea people have is, let's say we start with a normal red supergiant, and it starts exploding, just like before. So it had its core bounce, the material bounced off the core, the shock was sent out, the envelope's getting unbound. Looks like it's about to explode. But maybe because the explosion was a little weak, or maybe because the star is a little too massive, it's not able to overcome the gravity of the star, and instead the material collapses back down, collapses, and then a sad little event, right? It just disappears. The star's now gone. So this is one idea of what the birth of a black hole might look like. Basically, the implosion of a massive star instead of an actual explosion. And so this goes by a name of a nova, right? So it's not a nova, it's an unnova. And you laugh, but there's actually efforts to test this by looking at lots of close by massive stars, looking at them over and over again, and waiting to see if some of them just disappear. You look at enough, one should disappear eventually, right? Okay. But we thought about this more deeply and tried to think of maybe there's some other observational signature that should be associated with the black hole formation. And so let me talk you through this. Let's see how this goes. So let's look deep inside of a massive star. Here again is our hydrogen envelope. Here is our evolved core, and here's our iron core right at the center. Okay. And this neutron star, this core at the center, is very, very hot at these times. It's something like 1 billion degrees. And what it does is it produces, I'm getting too excited, it produces these ghostly particles called neutrinos that start emitting from this core. And if you know anything about neutrinos, their claim to fame is they're very, very weakly interacting, right? They basically can pass through anything once they're created. They don't interact. And so these neutrinos stream away, carrying energy from the neutron star. And we know from Einstein that E equals mc squared, right? So as they carry away energy, they're carrying away mass from that neutron star. And so what you actually expect to happen is that neutron star starts shrinking slightly in mass during this time. Okay? The neutron star's gravity now decreases because it has less mass, and the envelope sees there's less mass in the core, and it starts expanding a little, right? There's a little less gravity it's feeling. Okay? And this is all expected to happen before the core collapses to make a black hole. And so again, what we did is we turned to our computers and ran a simulation of understanding as this envelope adjusts a little bit and starts expanding, what do you expect to see from that? And so here's one of our simulations again. This is the velocity of this disturbance going from the inside of the envelope to near the surface of the envelope. And here you'll see what kind of light curve is observed. So let's start running it. And so it's kind of proceeding very slowly, right? This disturbance is moving up toward the surface of the star. And suddenly, though, it hits the very surface, and there's a flash of light. All right, so let's look at this one more time. One way to think of this is it's almost like this ocean wave moving toward the shore. And it's getting shallower and shallower as you're getting toward the shore. And eventually, that ocean wave breaks, right? And when that happens, there's a flash of light from the energy being released at the surface of the star. And so I wrote this up in a paper called Taking the Un Out of the Unnovae, right? Because now we actually expect that even in the case of a star that will eventually collapse to a black hole, that you still expect to see this flash of light. Okay? And this paper was pretty fun. It got a lot of press because this was a new way that we might actually be able to observe black hole formation in our universe. Now, I wish I could end the story here with telling you about how the observers went out and found these flashes of black hole formation. But unfortunately, one of the frustrating parts of being a theorist is the observers don't always find what you want them to find. And so they're still working on it. But I think it's only a matter of time, right? And honestly, this is probably one of the best times to find things like this. The this kind of event that we predicted, instead of lasting for a few weeks, it's only lasting a day or so, and it's somewhat dimmer. And so it's not unexpected that you wouldn't be able to find something like this. Okay, it's not as grandiose as a giant supernova. But this is really the ideal time to be finding this. There's new surveys going on just right now that are ideal for finding new types of explosive events. And one of my favorites I'd like to highlight is the All-Sky Automated Survey for Supernovae. Goes by the acronym ASSASSIN. This is a postdoc at Carnegie, Ben Shappy, who's one of the leaders of this program. And what they're actually doing is they just have these off-the-shelf telephoto lenses. They have one set up in Chile, one set up in Hawaii, and they're continually scanning the sky, making sure they don't miss anything going bump in the night. Okay? And so you can just see, it's really impressive just watching. This is a movie of the coverage of the sky they're getting over time, over the last few years. And as the colors change, this is the number of observations at each location on the sky. And you can see by the end of the movie, there's some spots with over 1,000 observations. Okay? And this is only going to get better. They've just gotten a new grant to build more of these units across the world so that they can scan the sky even more continuously and make sure they don't miss anything like the important things that I'm predicting in my theory. Okay? So this is all talking about mostly events outside of our Milky Way, right? These are our other galaxies that we're talking about. But of course, our galaxy should have a supernova once or twice every century. So the last time our galaxy has had a supernova that we actually were able to observe, there was two, one in the year 1572 and the other in the year 1604. So this is over 400 years ago. We need another galactic supernova. I mean, it would just be fantastic, right? If you can imagine going out at night, or during the daytime, let's say, and seeing a new star on the sky during broad daylight. Wouldn't that be just incredible? And just with all the new technology we have now, you just imagine how much better we'd be able to study an event like this. But so far, it hasn't been meant to be, I guess. We're still waiting. But we have our best guesses of, there will be a supernova eventually. What's the star that's going to do it? So some of our astronomers' favorite ones. So one of them is this star called Betelgeuse that you may have heard of it. This is in the constellation Orion. You can see Betelgeuse forms one of the shoulders. And so this really fits actually all of the properties of a red supergiant like we were talking about before that should make a type 2 supernova. Okay, so this has a mass something around 12 to 15 times the mass of our sun, a radius something like 900 solar radii, so it's this big expanded red supergiant already. The problem is we're not exactly sure when the supernova is going to happen. When is the star going to exhaust its fuel? Is it going to be tonight? Is it going to be 10 years from now, maybe 100 years? In terms of astronomical timescales, that's not too different, but for the humans that are patiently waiting on Earth, it feels like an eternity, right? But this could be the next supernova right here. And wouldn't it be glorious? You look up at Orion, and it looks like he almost got like shot in the shoulder when there's this explosion right there. Another star that we think might be the next supernova is called Eta Carina. And so this is around 7,500 light years away. And you can see it's a mess. This region actually had an outburst in the 1800s called the Great Eruption that wasn't quite a supernova. It was kind of a smaller explosion, maybe heralding the next explosion that's going to start, maybe next week or something. And in fact, there's not even just one star here. We think there's at least two stars. One of them's around 100 times the mass of the sun, another around 30 times the mass of the sun. It's kind of hard to tell, actually, because there's so much stuff around here from that great eruption. Okay? And I can't even tell you what kind of supernova this would look like, if it would look like a type 2 or not, because it's just so messy. But maybe this is what's happening. Maybe the star is near the end of its life. It's having this violent activity, and pretty soon it might explode. We'll see. So I just wanted to leave you guys to finish up with one last thought. So here's the Milky Way, looking from above. And our sun is positioned somewhere around here. Of course, this isn't a real photograph, right? We couldn't take a picture of it. This is an artist's depiction. And we're something like 20,000 light years away from the center of the Milky Way. Okay? Now, the size of the Milky Way itself is something like 100,000 light years across. And remember I said that a given galaxy should have a supernova once or twice per century. That means in our galaxy already, there are over 1,000 stars that have exploded that we have not seen yet, but they've already exploded. We're just waiting for the light to get to us right now. It's on its way. So, it's not a matter of if we're going to see a supernova. It's just a matter of when that light's going to get here. So, thank you. How many years, the question is how many years of research went into this talk? By myself, or, the modern study of supernovae was really initiated by Zwicky in the 1930s. And then, like I mentioned, 1987A kind of really revolutionized supernova studies again and kind of brought us to the modern time. So, a lot of this stuff has been ramping up almost exponentially as technology is getting better. More people are working on these over the last 5 to 10 years.
You mentioned that I think it was neutron stars and the leftover cores, the iron cores.
Yes.
Okay. Are all neutron stars in iron?
No, so there's a whole other story and a whole other talk I can give on neutron stars. But what happens is that the neutron star, the iron core, as it's collapsing, becomes so dense that you can actually have reactions where normally free neutrons are unstable. You can't have just free neutrons floating around, they decay. But at these high densities, you can actually prevent them from decaying. And what happens is you actually have protons and electrons that are there's so much energy in those electrons from being at high densities that they combine with the protons and make neutrons. And so you end up with this very neutron-rich material, which is why they're called neutron stars. Deep inside the neutron star, we actually don't know what the constituents exactly are. Those are at densities that are so high that we can't do experiments in labs on Earth to actually test anything. And so we actually study the neutron stars themselves and their properties to actually try to constrain what matter is like at those high densities.
In the summer of 2015, there was an extraordinarily luminous event.
Yes.
And I've heard that it may have been a supernova, or it may have been a supermassive black hole swallowing a small star. I wonder where you place your money. And also, how far would such an event have to be from Earth to avoid catastrophic effects?
So the question was about this super duper luminous supernova that was seen last summer. And so just to give some background, there's different, I've kind of described to you guys the main two classes of supernova. These are kind of vanilla-ish supernova in the world of exploding stars. There is a class of superluminous supernova, if that's enough supers for you, that are something like 10 to 100 times brighter than the events I was talking about, but they're very rare. They're much less than 1% of the supernovae. And we think there's maybe exotic things like highly magnetized neutron stars inside of them that are powering these explosions, nothing like anything I described tonight. Even on top of that, there was an event in the news that was even more luminous. And this event was actually discovered by Assassin, so they got a lot of exciting press for this. Unfortunately, it has not acted like any supernova we have ever seen. It got bright, it got dim again, it got brighter, produce all this UV light. It's a very complicated light curve associated with this. And that's led some people to think that maybe it's not a supernova at all. There's another idea that of a thing called a tidal disruption event. And that's when you actually have a star, like our sun, or maybe a little more massive, that falls too close to a black hole that's at the center of a galaxy like this. So every galaxy, like even our Milky Way, has a supermassive black hole at the center that could be millions or billion times the mass of our sun. And if a star falls too close to that, it get ripped to shreds and produce a big amount of light. One idea is the superluminous supernova is an object like that. I don't really have, I don't know what I favor actually at this point. It actually doesn't fit either of these class of objects very well. It's very weird. I think it's more likely that it's a black hole ripping away a star because you can get much more diversity in that type of event because you can throw in different types of stars, you can have different massive black holes and get all different types of things happening. But people are still taking more data to try to understand it better, so hopefully in the coming year or so we'll have more information. That's a long answer.
You were explaining that with supernovas expanding and introducing dark energy, are there some competing theories of dark energy rather than introducing this incredible concept of 70% of the energy in the universe being stuff we don't even know about? Are there seriously competing theories?
So the question is about this dark energy that I mentioned. And so just to be precise, what was measured was the expansion history of the universe. And normally you'd expect if something was expanding like the Big Bang, it'd slow down with time, right? You throw a ball in the air, it slows down with time eventually, right? And what was found when they started measuring the expansion history of the universe is actually accelerating its growth right now. Okay, it's not just expanding, it's expanding faster and faster. The best explanation for that is there's some sort of repulsive energy in our universe that's associated with all space. We refer to that as dark energy. I don't know a good competing theory for that, but what we're trying to actually do is take more detailed measurements of how that expansion is happening to see if it matches the predictions for something like a cosmological constant or dark energy. And so hopefully in the future we'll have that, but that's something we still need to test.
Is there a safety zone for habitable planets from either one of these two types of supernovas?
Yeah, so it's a good question. Is how I showed Betelgeuse and Eta Carina. Are these our demise basically staring at us? So Betelgeuse is something like 600 light years away. The best estimate for kind of the rough distance you need to be to survive a supernova is something like 30 light years or so. I don't know if you're right at 30 light years, if life's still comfortable or not, but maybe you can survive it. But definitely if you're within that distance, things are pretty bad for you. There's a lot of high energy radiation that comes from the supernova that would destroy our atmosphere. It's kind of interesting. You ionize the atmosphere, which is a lot of oxygen and nitrogen, and you make a bunch of nitrous oxide, which is really great because as we're dying, we'll at least be laughing from all the laughing gas. But kind of the ballpark number to keep in mind is kind of 30, 50 light years away for surviving a supernova.
If you have a type 1 nova in a binary system, what happens to the companion?
So that's a really interesting question. So one idea is that supernova should slam into the companion, and you might get additional light right near the beginning of the explosion that would actually tell you that that companion is there. And that's actually something we're actively looking for. So actually with Ben Shappy, who I mentioned, we've written 2 papers where Assassin has found supernovae right within half a day of the explosion, and we try to see if there's any evidence of a companion there. And so far, there hasn't ever been any evidence seen. Now, it depends on the viewing angle. If the companion's between you and the explosion, you'll see the material spraying around the companion. You'll see a really big signal. But if the companion's on the other side, hidden from the explosion, you don't see anything at all. So some cases, even if there's a companion there, you don't expect to see anything. But that's actually something we're looking for right now with current observations.
So about how long did you say a supernova would, the brightest would last, that we would be able to see it a day, did you say, or how long will it be visible?
So if there was a supernova kind of nearby in our own galaxy, we could see it for a few weeks during the day.
So I don't want to miss it, and aside from looking out there, are there enough people that are surveying the sky that you guys will get out of?
If it's in our own galaxy, you'll know about it. Don't worry. But no, it'd be a very exciting event, so we would know about it. Don't worry.
For clarification, you talked about iron is kind of the foundation of when a blue star evolves into a red supergiant. You talked about earlier, nickel decays into iron as a stable atom.
Yes.
Is the core of iron because of that decay? And follow up, does that imply that iron is the largest stable atom available to a star?
Yeah, I think most people heard the question, but the question was that iron I was talking about in the core of the red supergiants, was that originally nickel? And yeah, so what generally happens is you're putting together things with equal protons and neutrons, like silicon, carbon, oxygen, all that stuff has equal protons and neutrons. And so when you burn that, you always get more stuff with equal protons and neutrons, including nickel-56. Now, in the core of the red supergiant, this is all happening during the course of normal stellar evolution on longer time scales so that the stuff, as it's going along, could turn into iron. In the type 1a supernovae, there's an explosion, so you're kind of instantly making a bunch of nickel, and then you have to wait for that 9-ish days or so for it to decay, okay, because you made it all at once. But it's happening in each case. And yes, so the most stable element that you can make in a star is basically iron 56.
The young person in the back there.
Are we green? Okay. Oh. So the question is, do we know the state of the matter in a neutron star? So I guess the short answer is no, but the long answer is we know about a lot of the different parts. So neutron stars are very exotic, and they have many different layers. So remember I said before, the neutron star has a radius of about 10 kilometers and a mass about 1.5 times the mass of the sun. I don't know how you can even picture that. That's so amazing. So neutron stars have multiple layers, though. So for example, they'll have an atmosphere. Our Earth has an atmosphere, right? That's what we breathe. But the gravity on a neutron star is so strong, the atmosphere is about 1 centimeter or so thick. Okay? Underneath that atmosphere, they have a crust. They actually have like a lattice crust, like a hard material, formed out of this neutron-rich material that's about the thickness of 10 meters. And then interior of that, they have a sea of neutrons. And then interior of that, we don't really know very well what it's made out of. There's a lot of theories that we're still trying to test. And that's kind of one of the really fundamental areas of study on high-energy astrophysics that people do. So if you like a lot of math and a lot of physics, someday that's something that you could study.
Nathan, answer the question.
What would happen if a supernova exploded behind a black hole?
If a supernova exploded behind a black hole. Well, it depends on the orientation. So one interesting thing you could potentially actually do is you could actually lens the supernova, which would be really cool. So, as you know, black holes bend light are able to bend light. If you had it positioned correctly, you could actually potentially bend the light around the black hole, and it'd act like a lens, and you'd actually magnify the supernova so that you could see it more readily. So that'd be one cool thing you could do. If they were more directly close to each other, my guess would that you'd have a lot of material falling into the black hole, and depending on the angular momentum of that material, as it swirled into the black hole, you could get an interesting bright event. And that sounds pretty exotic, but we actually think that sometimes, as if you had a white dwarf falling into a black hole like the center of our galaxy, that could actually trigger the explosion of the white dwarf from the compression forces of the black hole. So it's not as exotic as maybe it sounds, and people have actually done theoretical calculations of what something like that would look like, even though it hasn't been seen before.
Is life associated with carbon-based life, with one type of supernova or the other?
So the question was, is carbon-based life associated with one type of supernova or another? So definitely, supernovae are very good at making these elements that I've been mentioning, like neon, oxygen, carbon, silicon, and so forth. Whether or not those are now necessary for life because of that, I mean, things like carbon are atoms that are able to make a lot of different complex molecules, right? Because they have so many different connection points. And so it's not clear to me the chicken and egg there, whether it's necessary, life developed a certain way because that was what was available, or is chemistry such that you still need those same sort of elements to make life? I don't know what the answer to that is. I don't know very much biology.
When the supernova in the late 80s occurred, what were the effects of the neutrino bombardment on Earth?
So that's a really great question. So one of the things I talked about, right, is these hot neutron stars should be producing neutrinos. And that was before 1987A, that was just theories make-believe land, that these neutrinos should be generated inside a supernovae. And in fact, when 1987A went off, it was the first time we had neutrino facilities, so they have these things like large tanks of water where you can see neutrinos coming through. Sometimes they interact and you can actually see evidence for neutrinos. And so from 1987A, with these neutrino detectors, less than around 24 neutrinos were actually observed, which maybe doesn't sound like a lot, but for these weakly interacting particles, that was just like a field day of, oh my gosh, where are all these neutrinos? So that was actually a really important confirmation of this idea we had that you should have this neutron star being generated inside of a supernova. That was confirmed for the first time because 1987A was so close. And you can just imagine now, in the future, if we had an actual galactic supernova with all of our better neutrino detection facilities we have right now, we'd get so much more information. And those neutrinos, because they're so weakly interacting, the light has to bounce around. It diffuses through all this ejecta. Okay? And so you lose a lot of the fingerprints from the really interior stuff as it's bouncing around. But those neutrinos, they're generated near the center, and they just stream out, man. And so you see deep inside of the supernova from those neutrinos, and you're able to view things that you would never see with just light. And so that would be a really important thing if we had a galactic supernova.
I know we have a lot more questions, but I think we should wrap it up. But Tony will be happy to answer questions. If you have questions, please come up and talk to Tony. We'll see everybody in 2 weeks, where Andrew Watts is going to talk about simulation, more theory, about the creation of the Milky Way. And let's thank Tony again for doing that.